So getting the rate of a reaction isn't something terribly crazy, something we've been able to do for quite a while now. So scientists have done that for a long time. They've studied a bunch of different reactions, and they tend to see the same sorts of patterns when it comes to reaction rates. All right, and these are what we call rate laws. Okay, so again, after studying bunches of reactions, they see the same common pattern over and over again, where the rate of the reaction is equal to some constant K, what we call the rate constant, and this is unique for each reaction, times the actually, let me just say before we move on here, we're going to talk about a very simple reaction where we have some reactant A being converted to product. All right, so what we would call a unimolecular, or I guess that's not quite true, a single reactant reaction here. Okay, so anyways, the rate of these reactions is equal to some rate constant K times the concentration of that reactant raised to some power n, which we call the order of the reaction. All right, and out of all the billions of reactions that they've studied, 99.9% fall into one of three bins, where n is equal to either 0, 1, or 2. All right, so the rate of reactions are proportional to the concentration of reactant times some constant, which is unique to every reaction, but we can calculate it, we can tabulate it in books. All right, but then raised to some power, which we call the order of the reaction. All right, so first of all, before we go on, let's take a look back at this graph here. And looking at that equation, why does it make sense that my reaction rate is decreasing over time? Again, we start out with this very steep curve right here, but as it approaches equilibrium, it slows and slows and slows. We get a shallower and shallower curve. If we look at our equation here, can anybody see why? What's happening to the concentration of reactant over time? It's decreasing, and that rate is proportional to that concentration. So as that reactant's getting consumed, according to this equation here, this number keeps going down and down and down, then yeah, the rate of our reaction is also going to decrease over time. All right, so our goal is, given some data, we're going to calculate, or we're going to go out, and we're going to perform some experiments, and we're going to collect some data. We want to be able to figure out what the order and what the rate constant is for a given reaction. All right, that's going to be our goal, is to analyze a data set here and figure out what the order and the rate constant is for a given reaction. All right, so first of all, this is what we call, this data set that we look at is what we call initial rate data. All right, and what we're going to do is we're going to measure the initial rate of a reaction, the very first few time points, okay, so the initial rate of my reaction over here corresponding to this portion of the graph when it's going its fastest, when it's just starting out, all right? We're going to perform our reaction. We're going to measure that initial rate. But then we're going to perform it again and again. And what we're going to do is we're going to vary the concentration of our reactant at each time, right? So measure the initial rate of a reaction at various reactant concentrations. All right, and with that type of data set, we can plug this data in and figure out what the order of our reaction is and what the rate constant of our reaction is. Okay? Cool. So I'm going to give you a data set here. Concentration of our reactant A, 0. This means the initial concentration at T equals 0. And then the initial rate, so I'm going to vary this concentration of A. I'm going to do it at 0.1 molar, 0.2 molar, and 0.3 molar. And I'm going to measure the rate at each of these concentrations. All right, so for this particular reaction, I guess let's say our initial rate is in molar per second. All right, and again, my goal is to use this data here to solve my rate law for this reaction, to figure out what the N and the K is. All right, and again, kind of the crazy thing, it's not like it has to be this way. The universe is just being nice here. That 99.9% of reactions fall into one of three categories, with N either equaling 0, 1, or 2. All right, so before we go on here, before we do any math, we're going to sort of show this strategy that will always work. But for this particular one, it's kind of a little easier than it needs to be here. What do we notice about this rate as I'm varying my concentration of A? It's not changing, right? So in this particular reaction, the rate is actually independent of that A concentration. So then what value for N would give me a rate law that's independent of the concentration of A? 0, right? So because that rate is not changing, this must be what we call a 0th order reaction, right? Where that order is going to be 0, because of course anything raised to the power of 0 is just 1. So that drops that out of that to begin with. All right, but let's sort of develop this strategy here that will always work, okay? So how do we determine the order of a reaction? Okay, there's a little trick that we got to use to get the order of this reaction. Because currently, if we look at this equation, I got two variables. I got both my rate constant that I don't know, and I got my order that I don't know. Are we going to pretend like we don't know our order so we can develop the long way about how to get it here? All right, so I got two variables. We can't be solving many algebra problems with two missing variables, so we got to figure out, we got to have this special strategy that's going to help us out here. And what we're going to do is we're going to take the ratio of the rate law for two data points. Right? We got 3 data points up here. I'm going to pick just 2 of them. Oh, just the first 2. Who cares? Boom, boom. Okay? And what we're going to do is we're going to take our rate law for both of these data points, but we're going to take the ratio of those 2. So what that means is the rate of that first data point, we'll call it data point 1, divided by the rate of my second data point. We'll call that data point 2. Right? This equals my rate law, my k times a to the power of n. So k times the concentration of A at that first data point to the power of n divided by K times the concentration of A at my second data point to the power of n. So again, we said we had to have this special strategy here where we're going to take the ratio of two data points. Why am I going to do that? What happens to my algebra equation here? How can I simplify this? I can get rid of k. I got k at the top, k at the bottom. K is just a constant value, right? So the whole reason why we're going to do this strategy of taking the ratio is because it gets rid of one of our variables that we don't know. We can get rid of k here. Okay, so because of that, we get to cancel k. We'll go back and figure out what that is at the end here. All right, the other thing that we're going to take advantage of is just some algebra here. The fact that x to the n divided by y to the n is the same thing as x over y all to the power of n. That'll let us bring that exponent out. So all of this is going to be equal to the value of a at that first data point divided by the value of a at that second data point, all to the power of n. All right, and all we're going to do is we're going to plug in our value from our table here, but I like doing algebra with symbols here. I don't like numbers in there. So bottom line is, what are we solving for here? N. So let's rearrange this equation to solve for n, because it's kind of a pain in the butt, because n is an exponent now, so we got to bring n down. All right, so first of all, let's just summarize what we have. All right, and now we're going to do another sort of algebra trick here. As my former algebra teacher used to say, in the magical world of logarithms, if you have x to the power of n, and you take the log of that, that becomes n times the log of x. All right? Yeah. I promise it's true. It's not the most intuitive thing in the world, though. Log algebra is a pain. All right? But yes, this is the trick that we're going to use here. And remember, we could do anything we want to this algebra here. I guess I can leave that. As long as we do it to both sides. We can do anything we want to this equation here, as long as we do it to both sides. All right, so what I'm going to do is I'm going to take this equation here. I'm going to take the log of both sides. So I have the log of my two rates equals now n times the log of my two concentrations And remember, despite how big and ugly this is right here, this is just the log of some number divided by another number. It's just a number, right? So I can divide both sides and simplify to get that value of n. All right, so everybody take a second. Using this data table, so we said ratio of two data points. We'll say also log Bring n down. That was our strategy. All right, everybody take a second. Using this data table here, plug those values in for the rate of our two data points. That's over in this column here, the rate column. And the concentration at those two data points. And see what value for n we get. All right, so all I did was grab those rates from my table, grab those concentrations from my table. All right, this is the log of 1.05 divided by 0.05. And the log of 1 is just 0, which is how we get a rate order of 0 for this reaction. Okay, so we've determined our value for n here. All right, but now we want to figure out what our actual rate constant is for this reaction. So how are we going to get that? Well, now we know n. We know n0. So we only got one missing variable in this equation. So now we just got to pick one data point and plug it into our equation here now that we know our order. All right, so we can just say, to determine that rate constant, we're going to plug in our order for this reaction, the n, and the values for one data point. All right, so I know that this reaction rate is equal to K times the concentration of A to the power of 0. So I'm just going to go on to my table. I'm going to grab one of the values for my rate and one of the values for my concentration of A. It doesn't matter what data point you pick. 0.05 equals K times 0.1 to the power of 0. Again, anything to the power of 0 is just 1. So I get my 0.05 is equal to that rate constant K. All right, so again, first type of problem we got here. We're going to use what's called initial rate data, where you measure the rate of the reaction at various concentrations of reactant, and we're going to use that to figure out what we call our rate law for this reaction here. The goal is to find what the order of this reaction is and the rate constant for that reaction. In order to get the order, we got to do a little bit of a special trick where we take the ratio of two data points, then we get our order, and once we get our order, we can determine the value of K by just plugging in the information from just one data point. All right, so let's do another one. Again, this is in molar. All right, so just like before, I'm going to take my ratio of my two rate laws. That will help me cancel out that unknown variable k. I'm going to take the log of both sides to pull down that n. Cool. So then plug this in. You could pick any two data points. You can just pick the first two. And when we get a value of n of 1, all right, that's what we would call a first order reaction. And now that we have that value of n, we can determine our rate constant k by plugging everything into our rate law. Rate equals k times a to the 1. Now we just need to grab a data point. Doesn't matter which one. Okay, divide both sides by that 0.5, and we get k is equal to 0.1436. All right, so that's how we fill in all that missing information from our rate law. We can determine the order by taking the ratio of two data points, plug everything back in to get our rate constant k. All right, now the last thing that I kind of been glossing over here are what are the units on that value of k. They're actually different depending on the order of your reaction. So that's our last step here, is units for our rate constant. Okay, so we don't know what k is. The units for k will actually depend on the reaction itself. But what we do know is that a rate of a reaction is measured in molar per second. Rates are always the same set of units. Likewise, our concentrations are always what? Molar, big M. Okay, so what we're going to do is we're going to plug this into our rate law using these units as variables, right? So we have rate equals k times the concentration of A to the power of 1 for this particular reaction. Well, if my rate is molar per second times k, and my concentration is molar raised to the power of 1, or just m, I'm going to rearrange this to solve for k. Just divide both sides by that big M. So I'm left with a k of units of 1 over seconds. So if I'm asking you for the units of our rate constant, what we know are the units of the rate and the concentration. K's job is to just square that all away, right? Make sure that the product of everything over here ends up equaling molar per second. And again, you're just going to plug everything in like a variable. So let's go back, let's rewind. We got our rate constant of k for this initial reaction here. Take a second and tell me what the units for that rate constant are. For a 0th order reaction. All right, so again, we're going to just use our rate law that we established here. But we know that our rate is in molar per second. That's equal to K times that concentration of A in molar, but raised to the power of 0. And again, anything raised to the power of 0 is just 1. So that means that my units for K must be molar per second. So if I'm being good, K is equal to 0.05 molar per second. So we can see that it's different for a 0th order reaction than it is for a 1st order reaction. It's going to depend on that reaction order. All right, cool. So that's all well and good for, reactions where you just have one reactant. But what if I have 2 or more reactants here? All right, so now let's look at a reaction where we have A and B combining to form some product. All right, how do we get the rate law for this reaction here? All right, so it's going to look fairly similar. Our rate is equal to some constant K times the concentration of A to the power of N times concentration B raised to its own order to the power of M. I guess I could have swapped those so it was alphabetical order, but it doesn't really matter. All right. So now we have 2 reactants, so our rate law is going to be dependent on the concentration of both of them, and our goal is still the same. We're trying to figure out what these orders are and what our rate constant is, so we can figure out what our rate law is for this particular reaction. So again, we're going to need a set of data, some initial rate data. All right, but now we're going to have to change not only the concentration of A initially, but we're going to have to do the same thing with the concentration of B. Both of these again in molar, and then our reaction rate in molar per second. All right, so I did this experiment. I collected some data. Oh, whoops, sorry. Not that it really matters, but this was okay. All right, so now we have a little bit more complicated of a data set here. We had to change not only our one reactant concentration, we also had to do the same with our second reactant as well and measure the initial rates at each of those conditions. Okay, and again, our goal is to solve our overall rate law here. So to get our rate order, in this case we got 2 of them. we're going to play the same game. We're going to take a ratio of 2 data points. All right, but now we got to be very strategic about which 2 data points we pick. Before, we could have chosen any 2 data points. It would have worked out fine. Now we got to be more strategic about the data points that we choose here. Okay, so first, we're going to select 2 data points where A changes, but B is constant. All right, so we're going to look at our table here, and we got to pick 2 data points just like we did before, but now we got to be strategic. We got to pick data points where A is changing, but B is being held constant. So that would be these first 2 right here. Right? My value of A is changing from 0.1 to 0.2, but the value of B remains that 0.25. All right, so these 1 and 2, these are going to be my first choice. So why is this going to be important? Well, let's do the same thing we did before. We're going to take the ratio of those rate laws. So the rate of that first data point divided by the rate of that second data point, again, is equal to my rate law here, equal to K times A at data point 1 times B at data point 1 raised to their respective orders, right? So A was raised to the power of n, B is raised to the power of m. And then we're going to do the same thing for our second data point. K times the concentration of A at that second data point times the constant raised to the power of n times the concentration of B at that second data point raised to the power of m. All right, now but just like before, what do we get to get rid of right off the bat? K. Good, because we don't know what it is. Boom. I still got 2 variables there, right? Still got n and m. So in order to be able to proceed forward here, I need to get rid of one of them. Well, remember, we chose data points where B was being held constant. So we just go back and plug that in here. Concentration of A at my first data point to the power of n times 0.25 to the power of m divided by the concentration of A to the power of n at my second data point times 0.25 to the power of m. What do I get to do? I get to cancel them out, right? 0.25, whatever m is, regardless of what m is, 0.25 to the power of m divided by 0.25 to the power of m is going to be 1. All right, so by strategically picking a data point where one is variable but the other is held constant, we get rid and down to just one variable here. Now we just have that order n. Okay? Cool. So we could go and do this the long way here, but let's be clever. We're going for the speed record here. My concentration of B is being held constant. That cancels out here. My concentration of A is changing, but what's happening to my rate of my reaction? It's being held the same. So what does that mean about the order with respect to A here? It's got to be 0. Okay? And I guess just to be clear, this we would say is the order with respect to A. All right, and we were able to just sort of logically looking at it here, figure out that that must be 0, right? Because that rate is not changing. And you could do it the long way and convince yourself. You could take the ratio of the rates to the log of the ratio of the rates divided by the log of the ratio of the concentrations, and you would indeed get that order n equals 0. Okay? So now we got to do the same game again. For the sake of time, we're just going to say n is 0. Boom. Now we got to play the same game, but now we need to take data points where A is being held constant and B is changing. So everybody take a second and figure out which 2 data points you're going to pick and see if you can't give us our order with respect to B here.
Just call this 3.
All right, so now I got to pick data points 1 and 3. When I take the ratio, K will cancel out like it always does. All right, but this will also allow me to cancel out A's concentration since A is the same at data point 1 and 3. So what I'm left with is just the ratio of the concentration of B at data points 1 and 3 raised to that order with respect to B power of n. And then we're going to play the same algebra game that we played before in order to bring that exponent down. Take the log of both sides. So I get the log of those rate ratios. Divided by the log of those concentration ratios. Plug in from my data table. All right, and I get that M, the order with respect to M, I'll give you guys a second to catch up. All right, so when I punch this into my calculator, the value for m that I get would be 2, or what we would call second order. Whoops, that's not how you spell that. All right, so I know that for this reaction here, my rate is equal to some constant K times the concentration of A to the power of 0, i.e. it actually is not dependent on the concentration of A, times the concentration of B to the power of 2. All right. Again, 0 is the order with respect to A, and 2 is the order with respect to B. We also have what we call the overall order of the reaction, which is just where you take the sum of those exponents, m and n. Since m is 2 and n equals 0, the overall order of this reaction would also be 2. All right, and we're going to call it there, but just to be clear, we could then select one data point and plug in to find that value of K. All right, and so for y'all, just for the sake of checking your work here, because we're out of time, the value for K that you would get would be 0.399, and those units would be 1/2 molar. But how did I find that? All I did was go in and grab one data point for my table here, plug in my rate and my concentrations, and use that to solve for K. Cool. All right, we got our rate law with our orders plugged in. We're going to still have to use our data table here, and now we're going to find that rate constant K. Well, at this point, we're down to one variable. We don't really have to do any tricks. We can, again, just pick any data point and plug in. All right, if we pick one of those data points and fill in that information, that'll be all everything within that equation except for that one missing variable K, and we can just use our normal algebra rules to solve for that missing variable. So everybody take a second and tell me what the rate constant for this reaction is. I'm going to pick this first data point here. It really doesn't matter. Again, just plug these into my rate law. So then I punch this into my calculator. My rate constant for this reaction is 0.399. 39904. We'll cut it off there. All right, so the last thing we got to talk about with respect to these rate laws is I've kind of conveniently left off the units for K. We got to think about the units for K here. This is going to be our last step. What makes rate constants kind of a pain in the butt is that the units for K depends on the overall order of a reaction. Reactions that have different orders will have different units for K. We can't just say K is always this set of units. All right, it's going to depend on the order of that reaction. What we do know, what is not going to be variable, is that rates always have the same units. We measure rates in molar per second, concentration per unit time, just like we defined it before. Likewise, we also know our units of concentration. What do we measure concentration in? Molar, big M. All right, so K's job in our rate law here is to kind of square the units from one side to the other. Rate has to be in meters per second. Concentrations have to be in molar. So K is going to be there to make sure that at the end of the day, this product has a unit of molar per second. All right, so what we're going to do is we're just going to take our rate law here and we're going to fill in our units as if they were variables, right? Because our units should all multiply and cancel out and all that jazz to be equal on both sides. All right, so if I just fill in my units here, I know that my rate, molar per second, I don't know what K is, that's what we're going to solve. I know my concentration of A has to be in units of molar, and that gets squared in my rate law. And I know B has to be in units of molar, but that gets raised to the power of 0, which means that it cancels out, right? Or rather, it's 1. All right, so K's got to be there to make sure that whatever this product is, has the units of molar per second. All right, so again, we're just going to treat these units as variables. Move over that m squared. That'll cancel one of them from the top here. Oh, whoops, just one. And I'm left with 1 over seconds molar. We get weird units for K. But again, K's job is to just square everything away so that the product on this side ends up having units of molar per second. All right, you can also see this written like more fancily or more compactly using negative exponents. Right, so actually let me move this over. This is the same thing as inverse seconds, inverse molar, right? Just using negative exponents. Again, fancy algebra. Cool. All right, so we have our rate laws. Again, all reactions that they studied, they follow this same pattern, where the rate of those reactions are dependent on the concentration of the reactants raised to some power, which we call the order of that reaction, multiplied by some rate constant. And by analyzing that initial rate data, we can figure out what those orders are, what that rate constant is, right? So we can predict what the rate of a reaction would be as we vary the concentrations of our reactants. Okay? Cool. So, if we carry out a reaction and we want to know the rate of the reaction, we can use our rate law. But what if I want to know how much of a reaction has actually occurred in a given unit of time? Like I mix this together and I want to know how much is left over after 10 seconds. That's very closely related to the rate of that reaction, but it's not the same thing. I can't just plug it into this here. Okay? Don't disobey me. Okay. So what we're going to talk about now is the dependence of concentration of reactant on time. Right? How much reactant is going to be left over after 10 seconds of this reaction? All right, so remember the rate of a reaction is the change in the concentration. So let's look again at a simple reaction here. A going to product. The concentration of A over the change in time. So the change in concentration over the change in time, that's what a rate is, right? The slope of those curves that we were looking at. We do this experiment. We measure the concentration of reactant or product as it changes over time. All right, so I'm measuring the concentration of H as it changes over time. The slope of that curve is my rate. But since it's a reactant, I got to multiply that by -1. Right? Well, remember, in fancy algebra speak, we don't do rise over run, or rather in fancy calculus speak, we don't do rise over run, we talk about derivatives. So negative d concentration of A over dt, that's my rate. All right, well, if I want the dependence of the concentration of reactant on time, what I'm talking about is the concentration of my reactant as a function of time. So in terms of calculus, I would integrate that rate with respect to time, and that would give me my function. All right, now, this is not a calculus class, so y'all can just trust me on this. If you went and took these rate laws and you integrated them, you did your calculus, all right? I don't know. I feel like it's not calculus 1. It might be 2 here because you got a function embedded in. It doesn't matter. But not a calculus class, right? So what we're going to do is I'm going to tell you what these integrated rate laws are depending on the order of the reaction, and you're just going to trust me that I use calculus to get there here. I took these rate laws that we had, right, that we were just filling in our variables for, and I integrated them in order to get my function, my concentration of A as a function of time. So this is what we call the integrated rate laws. And we call them that because we had to do some integration to get there. All right, and I'm not going to try to remember them off the top of my head so I don't mess up. Okay, but again, the whole shtick is these are concentration of reactant as a function of time. All right, and they depend on the order of that reaction. So for a 0th order reaction, the concentration of A as a function of time is equal to negative K times T plus A naught. All right, remember how when you integrate in calculus, you always got that plus C at the end, that constant at the end. This actually means that constant's not just a random number, it means something in the context of the reaction. It is the initial concentration of your reactant. Okay, so how much A is left over after a certain period of time will of course depend on how much you started with to begin with, right? And then notice that our rate constant features in this reaction as well. The larger that value of K, the quicker this reaction is going to go, right? We're going to consume reactant at a faster rate. So this would be for a 0th order reaction. For a 1st order reaction, the concentration of A as a function of time is related to the initial concentration of A times that magic number we get in calculus, E to the negative KT. This is what we would call an exponential decay. And then lastly, for a 2nd order reaction, so that's not how you spell second. That concentration of A as a function of time is related to the initial concentration divided by initial concentration KT plus 1. So let's just use this equation here. We found that this reaction that we were studying before is this 2nd order reaction. So let's just ask how much reactant is going to be left over after a certain period of time here. We went all the way to get our value for K here. Oh, and we can even say we got our units as well. So let's just say we have a 2nd order reaction where K is equal to 0.399. If the initial concentration of A is 1 molar, what is the concentration of A after 3 seconds? Right, so now I'm asking about how the concentration of A changes over time. So I'm going to use my integrated rate law. And I'm just going to plug in my variables from this problem. All right, and we're going to be good about our units here. So this was 1 molar. That initial concentration of 1 molar times that value of K, 0.399 molar per second, times time, our 3 seconds, plus 1. Okay, everybody take a second, punch it into your calculator. We see that our units will cancel out nicely to leave us with units of concentration, to leave us with units of molar. Everything cancels out at the bottom. The only thing that doesn't cancel out is that molar on top. All right, and plugging these numbers in here, making sure to put that denominator in parentheses so I don't mess up my order of operations. You would get that A has a concentration of 0.455 molar after 3 seconds. All right, so 3 seconds, not a large amount of time, right? Our value of K here, 0.4-ish, is actually a pretty large number. Any rate constant that's like 1 or above is a reaction that happens like that, right? Within just 3 seconds, we've already consumed half of our reactant in this reaction. All right, so K values tend to be pretty low numbers unless you're talking about reactions that are essentially instantaneous. All right, but these integrated rate laws here is how we would get our concentration of reactant as a function of time. Again, it's dependent on the order of that reaction, right? So in your rate law, what is that exponent? Right? All rate laws tend to have the same 3 exponents. The ones that we're studying, 99.9% of reactions have those same 3 exponent values, 0, 1, or 2. What is it here will depend on what integrated rate law you use. And again, that integrated rate law tells you the concentration of A as a function of time. Cool. All right, so the last thing that we can do with our integrated rate laws is what we call determine the half-life of a reaction. The half-life of a reaction is the amount of time required to consume half of the reactant present. Okay? So let's just think about this here. I'm going to show you how to do this for one of our integrated rate laws, and I'm going to leave it up to you to solve it for the other 2. All right, so let's look at how we do this here. It's a pretty simple strategy. If the initial concentration is equal to that A naught, that variable that we see in all our integrated rate laws, what is the concentration of A at the reaction's half-life? right? What does it mean to be a half-life? It means that half of that reactant that you started with has been consumed. So the concentration of A would equal A naught divided by 2, right? Just half of that initial concentration, nothing crazy. That's what it means to be a half-life. All right, so again, I'm going to show you how to do this for one of them here. We'll do it for a 0th order reaction. We know that for a 0th order reaction, the concentration of A as a function of time was this equation here. That was our integrated rate law for a 0th order reaction. So how am I going to find that half-life, the amount of time it takes for half of that reaction to be consumed? All I'm going to do is substitute in for my concentration of A, that concentration I'm looking for. And I just have to solve to figure out what that time is going to be at that concentration, right? So now I'm going to solve for T. All right, so everybody take a second, rearrange this equation to solve for T. All right, so I'm going to subtract that constant from both sides. All right, to be clear, that will give me negative A naught over 2 on my left-hand side, right? 1/2 minus 1 is negative 1/2. That's essentially that operation. That is equal to negative KT. So then I just divide both sides by negative K. I get that my time, we put a little 1/2 here to indicate that this is the half-life of this reaction, is equal to A naught over 2K. Right, and again, we can just note, like we said, as the value of K goes up, your reaction is quicker and quicker, right? And that checks out here as well. Our half-life is inversely proportional to that value of K. So the bigger number I put in for K there, the smaller my half-life is. The quicker it takes for that reaction to consume half of that reactant present. And you're just going to do this exact same strategy of plugging in to the integrated rate law. And solving for T to figure out what the half-life would be for a first and second order reaction. Cool. All right. Break.